Okay, good morning to everyone. Is everyone ready to in? At least my son is not ready to in. Haven't opened my phones yet. Uh, let's start with a hint on the assignment. Let's look at the question of the quotient group. The action by the quotient group. Which question did I get a question before? Question 4, right? So what did question 4 say? Suppose G acting on a set S set S, then we have the induced action G of N on S. What do you ask to show? What did you ask to show? Hmm? What is that? That's all. Uh-huh. So we have the action by the quotient group is faithful. If and only if, but sorry, n equal to the kernel. So kernel of what? Of what? P. We haven't defined. Okay, so the kernel of phi is n. But we haven't defined phi yet. What's phi here? Hmm? The homomorphism from when to when? Homomorphism from where to where? When P is a homomorphism from G to the commutation of S. The permutation presentation given by the action of G. Okay. Actually, there's one more word is not defined here. Which word? There's one more definition you need to know before you can solve this question. Any word here you don't understand of it? Which word is not defined or not clear to you? Which word? Which word? Find word, please. Yeah. English word, right? Which word you don't understand yet? Or haven't defined for you? Which word? Can you find a word that haven't defined for you? Yes, induced action. Yeah, right. Induced action. So what's induced action? Anyone start solving this already? Ziqian, you know what is induced action is? What's induced action? Okay. So induced action means what? Means you have an action, okay, and then you try to use this action to define a new action. Where's induced? So what is induced action here? Suppose G add on S. So we know that how every element, group element, add on the set element now. Okay, so the induced, and let's take a normal subgroup in G, then the induced action G mod n on X is defined by following map. I'll use C again, use another notation. G to what's going from G mod n cross X to X. How do we define this? So we take a coset, right? Element of the quotient group is coset, okay? And then I take an element in X. How do I combine them? I just take a representative, okay, and then add on X. And then this is not. This is given by how G add on X. Okay, so meaning what? I give you a concept, you just pick a representative and then add on it. So one problem here, there's a problem here, right? This is a specific element, but here there's a lot of things here, right? Imagine Z mod and Z. What is in the concept of 0? Z mod and Z. What are equivalent to 0? Listen, in Z mod and Z, what are the elements that are equivalent to 0? Yeah. Yeah. Sorry? N, right? You have 0, you have N. So 0 and N define the same concept. So I can pick 0 as my representative, I can pick N as my representative, right? So if I take 0 composed with X, is it the same as N composed with X? Right. So you need to check whether this is well defined or not. Okay. Okay, so I will help you to solve half of this question here. The way we solve half of it is to show actually kernel is a N is a kernel of subset. Sorry, N is a subset of the kernel. Okay, so let's prove this. So, I will show that. Let's show this claim here. The claim we will show here is G mod N define. Sorry. So G mod N. Okay, let me phrase it in this way. The induce action. Okay, the induced action by G mod N is is well defined. Okay, how about we face it the other way? So let me face this. Okay, the map Gmo n s to s define action if and only if, okay, if and only if n is in the kernel of V, in the subset of kernel of V, okay? And then if we define a faithful group action, then kernel of V is inside the norm. So this is the thing you need to show. The second thing you need to show for this question. Does that make sense? Make sense or no? Okay. So to define for the induced action, to define a really satisfy the group action, you need n is in a subset of kernel V. For the induced action to be faithful, you need the other direction for the kernel V to be in n. Okay, so we will show this direction for you, so that we really define a group action using this induced method. Okay, so let's prove this. We do the backward direction first. Okay, so meaning we suppose n is in the kernel of V. Okay, sorry.
So this n is equal only or not equal to 1?
Subset. Yeah. Yes, only subset. So the other inclusion, you need it for faithful group action. Yeah. Makes sense? If it is equal, then we don't need faithful anymore, right? We can just throw everything. Yes. So if you define a group action, then you need the other inclusion, which is what is in the assignment. Okay, but to define a group action itself, you need one inclusion. Okay, to start with. Does that make sense? This is just statement. I haven't tell you why is it true. Get the statement right first, and then we will verify whether it's true or not. Okay. Does everyone get this statement right? To define a group action, if and only if the normal subgroup is in the kernel of V. What is the V here? V is the permutation representation defined by the group action. Okay? Okay. Is it clear what we want to do now? No. I see you a lot of confusing face, but there's no question. So I cannot help you, you know. Yeah. Yes. Yes. So if you want to show that group action is a faithful, then you need to show the other inclusion. Okay. N is a subset of kernel V. Is because the map define a group action. The induced action is really a group action. Okay. Okay. So what do we need to check here? So we need to check that this map really define a group action. So you need to first check that this definition is well defined, and then you need to check the two group action axioms. Okay. But I would say that the group axiom is easy to check because your n is normal. Okay. The harder part or non-trivial part is this definition is well defined. Okay. So let me write it up. First, show that this phi map is well defined. Okay. So how to show this map is well defined? And how to show that this map is well defined here? Suppose G1n equals to G2n. Right. How does the map well defined? If x equals to y, dx have to be equal to dy. Right. So we take two equivalent cosets. We need to show that G1 star x equals to G2 star x. Right. For all x. Okay. Make sense? Does it make sense? If not, please ask them. Okay, you need to make sure that each step need to be connected. This is how you learn. Okay. But I realize in Asia, how you guys learn, at least from the way you guys ask questions, you like to see big picture. I was like that last time. You like to ask about concept. There's no wrong about that, but this is a new skill I want you to learn from me at least. What's the new skill? Please learn by logic as well. I don't ask you to throw away your big picture, but please gain a new skill that you can learn by logic. Make sure each step is connected. Okay, so we want to show that G1x equals to G2x. We know that the two cosets are the same. Right. What can we deduce from here if we know the two cosets are the same? Remember the TFAE segment? If two cosets are the same, what can we get? G2 minus 1 G1n equals to n. Meaning what? Meaning G2 inverse G1 is in n. Okay, but what is our assumption here about n? N is a subset of a kernel of phi. So this G2 inverse G1 here is in the kernel of phi. So what does this mean here? What does it mean? Meaning what? You look at the permutation representation. Where should the G1 inverse G1, where G2 inverse G1 go? Go to the identity map. Okay, right. Identity map that fixes everything. Okay. So it goes to the identity map that fixes everything. Okay. Well, so meaning what? That is G2 inverse G1 on all the elements is equals to the identity acting on all the elements. Right. Have you seen our goal reaching soon? If we got this, what can we deduce next? Ginseng. Multiply G2 on both sides, right? So I can add more element by G2, for example. On both sides. But this is just G1 acting on X equals to G2 acting on X. Okay, but here not that we only use property of groups. We don't use action yet. Okay, I mean we should use property of action. Okay, but this property of action is the from the group action already defined. Okay, so by the group action on by sorry, so I'll try to write it. So by group action G acting on X. Okay, because we know that G define an action. Does it make sense? Okay. So we can combine these group element within G. Okay, cannot. Okay, so this prove that the induced action is really well defined, and then we need to check the group axiom, right? So still need to check the two group axioms. Still need to check the two group axioms here. So first is what? You take the identity coset in G mod n, right? Okay, so let's remind ourselves what's the group action we want to check. So it's G mod n on S. So the identity in G mod n is the identity coset. Okay. So we want to prove that this new action here. So do I give a name? Okay, no, yet. Never mind. So just give V1 here. So this map here should give me X for all X. And then if I take AN, BN, use the induced action, I should get BN acting on X first and then acting by AN. We need to check these property. And I claim that these are obvious by definition. So you should try it. Why is it obvious here? So this action by definition is what? When we have a coset acting on X, we define by just take the representative and add on the element. Then you return to the normal action where you get X always, okay, if you compose with identity. How about second one? This is by definition what? You cannot use definition yet because your definition only define a coset. So is this a coset or not? Is this a coset? Say yes. So, who say yes? Huh? Anyone say yes? Is this a coset? AN, IBM? No, I say yes. No. In general, it's no. But this N is what? We can only slash out by a normal subgroup. So when the subgroup is normal, every left coset is a right coset. In particular, you can use the same representative. So NB equals to Bn. A, B, and N is a left coset. They're represented by AB. So you should make A and Bn a coset first, and then you add on X. Then you can use definition. This is just the representative acting on S. Then you use the group action on G to split them up. Okay, and then you use the definition again to return back to your AN, the group action on X by the quotient group. Let me be precise here. So here's 1, and then I get Bn acting using the quotient. Make sense? Okay. Okay, so mathematics is really precise. You need to lay out everything. Okay. So when I say this part is easy, because you don't even use the assumption here. Okay, so this assumption is for well-definers. And then to check group axiom, it really follows from the group action of the original group. Okay. So once you get your definition right, things should be easy. How about the other direction? How about the other direction? Suppose you have an induced action. So we have induced action, it is well defined. All the group action axiom are satisfied. We need to show that the normal subgroup is in the kernel of phi. Show that the normal subgroup is the subset of kernel phi. Okay, so subset inclusion, how to show? Take element from the left hand side, show that it is an element in the right hand side. Okay, so now you need to show that something is in the kernel of phi. What does it mean? What does it mean? So take an element, let's say little n in n. We want to show that. So the goal is to show that n is in the kernel of phi. That is, in the permutation representation, n is get sent to the identity. So we're going to check this, whether this is true. So it means like the n act like an identity of everything. So how to show this? Then you need to look at the definition. Right, look at the definition. How we relate the induced action to the group action. So n is in n, right? Okay. Observe that n define the same coset as n define the same coset as u. n. And then apply the definition of the induced action. What do you get? Then for every s in X, what is n star s? They define it defines the same action as En star S. But what is En star S? It's just E on S. E on S is what? It's just S. So NN define the identity map. Okay. Okay. Are we close yet? On the other hand, by the definition, hey, hello, Siri. We got a person there. Second Siri. Okay. So you have like listen to a podcast. Abstract algebra podcast. Okay. On the other hand, by the definition of the quotient group, okay, group induced action of quotient group, what is N star 1x? This is by definition one. What identity? By definition, okay, let me put a dot here. Definition is what? N on S. Okay, you show that this is N on X, this is also equal to X. So together you get N star X equals to X for all X. And then what is this? This is just the identity map. And just the identity map. What is the thing that you compose with X? You always get X. Is the identity map. Okay, no? Okay. Yeah. So this done half of the job, just to define induced action. And then to see that this action is faithful, you need the other direction that kernel of V is a subset of N. Okay, if you know. Does that make sense? Okay or not? Any other question on the assignment? Is it possible to hand in tomorrow or not? No. How's the progress? How's the progress? You left a big question too. How about the rest? Huh? And this one. Okay, 2 questions. How about the other? How's the progress? How's your progress? Haven't started yet. Okay. So how? And so how? Next Monday is a public holiday, and then so next Monday is a public holiday. You want to take the public holiday to do assignment, is it? Yes. Jayes said agree. Can't agree more. Don't agree more. Yeah, so I mean the question 2 is kind of challenging. So question 2 is about X3 acting on 2 element set of order 3. Okay. And then it doesn't tell you what the action is. Okay, I'm trying to give in on question 2. Please listen carefully. So question 2, you have a S3 action on the 3-element set, right? It only tell you whether it is transitive or what is the orbit. But it doesn't tell you what's the action. But the easiest action you could think of is just permuting them, right? You just permute them. So how to classify all these actions here? Okay, how you classify all the action to permutation? Okay, how you classify all of them? I suggest one way to see it is to determine what's the kernel of phi. What kind of kernel of phi can take? Okay. Remember, every kernel is a normal subgroup. So how many kind of subgroup in S3?
6.
6. So how many of them are normal? Only 3 of them. You can check. Okay, all the other 2 subgroup are normal. So if 3 of these normal subgroup are the kernel of the computation representation, what kind of action they give you? This is what you need to think about. Okay. For that question. So if you can't get it, so please come to my office hour today or Friday. So in this case here, let's postpone the due date to next Tuesday. Is it okay? Tuesday midnight. Next Tuesday midnight. I give you 5 more days to do it. Okay. But still, please do it properly. Okay, please do your assignment properly. Please spend time doing it. And then I will release the last one also. Okay. Because we don't have much time. Please don't delay on the last one. Otherwise, you won't get feedback. Because there will be exam question. You need the last assignment to do it. Please don't delay the last one. Yeah. And then, yeah, basically that's it. So next, since we talked about next Monday is a public holiday, right? So Friday will be the replacement. Then 3 to 5. Depending on the speed, maybe I will go a bit longer. But also on that day, there will be seminar by the first year, Calculus 2. So all of you are welcome to come to listen and then participate in the seminar. It's in A3618. Okay, you could come. When they have all the topics ready, similar to last time, I will send out the invitation, the formal one, to all of you. Okay, and you can come and see how they perform. All right, and maybe Jinko will give in a performing. Maybe I don't know. Maybe.
How about you?
It's a surprise. Huh?
The subject 3, man?
Subject 3. So which one is the subject 3? So we got an idea like if the senior go right, should the senior perform or not? Perform the subject 3. TikTok dance.
You how many money you?
Huh? What money you want?
You how much?
I don't like that. Everything talk about money only.
I allow give their worker who done this about 10K plus.
10K plus. Okay. Okay. All right. Okay. So any more question about assignment? Yes.
So the fourth question is defined on the number.
you mean by define of normal subgroup?
The n means the normal subgroup.
Yeah, you can only take quotient of group by a normal subgroup.
Oh, yeah.
So it must be normal. And also not normal. Possible. But I thought just now we use but just now when we check the group axiom, right, we need the normality of n. Maybe we can look through it again. But at least from our argument just now, we show A and B and add on x, right? We need the normality. Maybe we can have a look on that statement during my office hour. Okay. Yeah. Okay, if not, let's continue with ring. Okay, remember that last time we talked about the homomorphism, ring homomorphism specifically. What's the example of ring homomorphism? One very important example is the evaluation of polynomial. Okay. Let's say what? Polynomial in R x and let's say alpha in R. Okay, so what's this? What does this mean? So give you a polynomial. Okay, you can give me some number. I'll put some number. So what do? I take a polynomial. I just evaluate x at a. Okay. So this is one very important example. You should show that this is really a homomorphism. Okay. Okay. Oh, the other thing I want to talk about learn by logic, right? This is really related, connected to how you study. You want to see big picture. What does it mean? You want to see the full theory. But in this research frontier or what we did now, there's no full theory. There's no full theory. If there's a full theory, we don't need to research anymore. So what you need to learn in university, very important, is how to correct yourself using logic. Because I find it struggle when I do research at first. Because I am also like you. I want to see full things. I want to learn everything. But it's impossible. And then only when I want to finish PhD, only I found how to do research. So how should I do research? So we just learn whenever we need to learn. It's not that I need to learn everything first and then I can do something. It's not like that. This is actually not how you learn. Maybe perhaps it's because our high school education or pre-U education is, how to say, is too rigid, I'll say, not as free. Because you need to think about it. So for example, primary school or secondary school, like in Malaysia, the primary school, you have to study until 12 years old. This is what in Chinese they call it 义务教育. So in China, how many years you must study. You must study. 9 years. 9 years. For us, it's 6 years. Okay. So if it is must, everyone must study, that means what? The standard must be pulled down until that everyone can accept it. You get what I mean? So this is the consequence of that. Everyone must study. So you must make everyone accept the knowledge. So you need to make it as easy for everyone to study. Okay. So, but this is not the case here, right? You study based on your interest. Okay. It's not like I force you studying here. Okay. No. I'm not forcing you studying here. You could live any time you like, actually. Right? This is not 义务教育here. We study as we like. Okay. Yeah, so please change your mind. Okay. From a fixed mindset to a growth mindset. Your mindset should be growing. Okay, you cannot fix. Okay. So speaking about this example here, we will introduce a proposition which is called the substitution principle. Okay, so what's the substitution principle here? So let's take a ring homomorphism. Okay. So how should you imagine this ring homomorphism here? You should imagine that as most typical example is let me write here. For example, this V could be taken from Z to C. Okay, you take it as an inclusion or a subring, okay, sitting inside C as for Z, right? So you can think of this as an inclusion map, or you can think of it as, for example, between C. What can you play around between C? You can use the conjugation map. This is what's your name again? Yeah, behind is your what's your name again? 雪妍 beside 雪妍 雪梅 right? Yeah, Xue Mei talk about this conjugation here. So we can use conjugation to turn my scalar field. Okay, not scalar, okay, just ring. Okay, so these are the example of this ring homomorphism here. So what can we do with them? Okay, so we can take an element from the codomain ring. Then there is this unique homomorphism, big C, capital C, from the polynomial ring of Rx, okay, to R prime. So what do? We just send my X to alpha. We just evaluate it like just now, okay? But not that, see, I don't tell you what happened to general polynomial. I just tell you what happened to S. Okay, I don't tell you what happened to general polynomial. I just tell you what happened to S. Huh? That agrees with the map T on the constant polynomial. Why is this possible? If I just tell you what happened to S, how do I determine what happened to S squared? How should I determine what happened to X squared? Sorry? Why is it? Okay, alpha squared. So Jimbo said we should send X squared to alpha squared. Why is this true? X times X, but X live in a different world with R prime, right? So how you connect these two worlds here? Maybe. So where should x squared go? It should go to x squared. But how do you make sure that x squared go to alpha squared? Given that you know x go to alpha. Then it's going from the polynomial ring adjoint x. We know that x should go to alpha. So how to determine this alpha squared to x squared to alpha squared? Okay, how to see? So you need to talk about what is capital phi of x squared. What should this equal to? Yes, yes. So what are you using? What's the property here? Phi is a homomorphism. Okay, so this word is very important here. It's not just a random map. It should be a homomorphism. Okay, so meaning phi have to satisfy phi x squared to satisfy phi x times phi x. And then we know where phi x should go. It is just alpha. So alpha dot alpha is alpha squared. Okay. How about in general? How about in general? Maybe x plus 1. What should this equal to? Sorry? What should this equal to? I speak up, speak up. Speak up. What should phi x plus 1 equal to? Phi x plus phi 1. Why? Because again, it is a homomorphism. Okay, we want to extend this map to a homomorphism. Okay. Phi x is alpha. How about phi 1? Why? Okay, correct. Good, very good. So that agrees with the map phi on the constant polynomial. So it means that it sends all the element in the coefficient, in the ring to itself. Okay, good. So we have homomorphism. So this homomorphism is very important here. It will help you to extend the map. And then what do you do to the constant polynomial? You just fix it. Or I don't mean you fix it, but it depends on your phi. Depend on your phi. Okay, it just depends on your phi. So I think I should keep it. So just depend on your phi. Because you see there are two kinds of phi here. You can play with your phi. Okay, you do conjugation, or you just do inclusion. Okay, these two types. Okay. You can do something with your rings. Okay, you can solve it like conjugation on complex number, or you can do just inclusion. Does that make sense? So depend on your small phi here. Okay, so here should be kind of small phi. Okay. And anything we need to check. And then this is unique. So here it says that this is unique. Okay, why is it unique? Because I already tell you what the definition of your map is. And this defines the map uniquely. Okay. If you have two different phi that give you the same evaluation, you actually start with the same map. Okay, this is the uniqueness there. Okay. So the idea of this proposition is, if you want to define a substitution, okay, map from a polynomial ring, you just tell me where the x should go. Okay, you just tell me where the x should go. And then all the rest is extended by homomorphism. And then on constant, you need to know what's the ring homomorphism you have here. Okay. Okay. So typically, usually if we don't play tricks, it is just inclusion. But sometimes in number theory, maybe we need to play some trick. Okay, we need to do some conjugation, swap between root of unity, something like that. Okay. So you should see that I to minus I is some swapping. Okay, it's just conjugation. Swapping of a root of unity will be something else. Okay. Okay, so this is just one variable, right? So we actually can extend this idea here to multiple variable. So, yeah. So we can extend this idea to multiple variable. So, okay, how about we just go forward? So more generally, we can do n substitution. Okay, let's call it alpha 1 up to alpha n. Then there exists a unique homomorphism phi from R adjoint n variable to R prime. Okay. Similarly, what happened to your constant? Okay, it agree with the phi map. You agree on the phi map. So usually this phi map here is just identity or inclusion, but sometimes we can do conjugation also. Okay, we can play around with the constant. Okay, so let's look at some example here. Okay, we have learned some ring map, right? So for example, take Z to Z mod P, okay, or the field with P element. Does anyone try to show this? Okay, when P is prime. Does anyone try to show FP is a field yet? Anyone try? Right? Have anyone tried to show why FP is a field? Huh? What is a field? Right, so recall what is a field. Yeah, recall what is a field. Field is just a ring. But if it is just ring, why is it called field? So what's the difference? So in other words, all the non-zero elements are unique. So meaning other than the zero there refers to what? The additive identity. Other than the additive identity, all of them are multiplicatively invertible. Okay. So when P is prime, what's going on? Actually, we have go through the details when we talk about groups. When does Z define the groups? When does Z mod PZ define the group? Or Z mod NZ define the groups? How to define addition on Z mod PZ? How to define multiplication on Z mod PZ? And then why all the non-zero element? When does all the non-zero element are invertible? See? See? This is really, where is this? This is the lecture 2. Lecture 2, what did we do? We define addition on Zn. Okay? And then it forms a abelian group. And then we check that it is well defined. Okay? And then I challenge you to go back and define the multiplication. And before the class finish, means you give this piece to me. I hope you guys do it yourself also. If not, at least read about it. So you also can define a multiplication. okay, on Z mod PZ. But when does the non-zero element have inverse? We also talked about this before. Yeah, see? When does M invertible in Zn? Okay, only when M is a coprime with M. So if you want to have all the non-zero element invertible, that means it has all of them has to coprime to that M. So when you can achieve that? Only when your P is prime. Because if your P is prime, only prime and 1 can divide it. All the other numbers are coprime. So Zn with multiplication is a group only when n is a prime. So field means what? In other words, a field has to be a abelian additive subgroup and multiplicative subgroup. Depend on non-commutative and commutative. So it is both group in the sense of additive, addition, and multiplication. Okay, that is field. And then later we will see actually field is much easier than ring. It's easier to read. A more complicated object is rings. So the general idea for rings definitely work for field. Okay? So we just have ring theory. There's less on field theory, but we can do other stuff on field theory, like field extension in abstract algebra too. Yeah, so you see, so I cover a lot of pieces here and there. So you should try and put them together now. Okay, put them together. Okay, so let's have this map here. What's this map here? Integer to FP. It's just taking 1 to 1 mod P. Okay, modulo P. Then, what can we consider here? So let's define another map. Define another map. The substitution map from Zx to X. We can look at this map here. Oh. Okay. And then what's this map here? Okay, given phi, what can we do? What can we do to the polynomial in terms of Zx? What happened? Okay, how about this one? Let's call this another name first. If you have phi, right, that reduce Z to Z mod PZ, what kind of map you can define between these two rings here? So you have Fx. We do it step by step. So what happened to this? What can I do to this polynomial here? So these AI are in Z, right? Okay. And then I have a map from Z to FP. What can I do to this polynomial here? I can reduce the coefficient mod P. Okay. So I can send all this coefficient here to mod P. So how do we denote mod P? Usually we just put bar. Okay. And then we will write this F bar X, where is AI bar is equals to AI mod P. Okay. And then this is what we call the residue of fx mod p. Okay, we will call the residue, we will call f bar x as the residue of fx mod p. Okay, so residue is what? Something left over. Okay, so if I reduce the coefficient mod p, then the resulting function is something left over by fx mod p. Okay, so this is a notation terminology. So what can you do for the substitution? You can send your x to any element in your FP. Okay, you can just do some evaluation. Okay, and then when you do the evaluation, the coefficient here will get reduced for P as well. Okay, does that make sense? Can you imagine what is going on? Yeah. If you can't, you can ask. Do you want to see specific example? Or... Yes, yes. Okay, Vincent say yes. Okay, let's go specific down one level. So, for example, let's look at the phi of Z to F. Okay, let's look at this. And then we look at the ring homomorphism from Zx to okay. And then what can I do? So by the theorem, there's a unique homomorphism if I tell you where the x should go. So go to where? I'm going to go to 3. There's no 3 here, right? There's just a 0, 1, 2 here. 3 is equivalent to 0. Maybe we can send to 0. You want to send to 0? Okay. If you send to 0, then most thing gets sent to 0. Suppose, for example, we can see what is s squared plus 3x plus 5. Where should this element get sent to? Huh? This element should get sent to 0 squared plus 3 mod 3. You get 0 times 0 plus 5 mod 3. You get 2. So this element, this polymer get evaluated to 2. Sorry? What is phi of x squared? Px times px. What is px here? 0. So 0 times 0. Yeah. Makes sense? But what are you really doing here? You are seriously just substitute the 0 inside here. 0 squared. That's why we call it a substitution principle. But we rephrase the substitution in terms of ring or homomorphism. But the result is the same as you substitute 0 here. You substitute 0 here. Make sense? So this step here is substitution. So whenever you do substitution in your mind, you are making a map. Make sense? Make sense or not? Okay. No, define. This is definition. We define. Yes, we define it. If you send to 1, then there's a different ring homomorphism, different substitution. Just define it. Okay. Yeah, so you need to make very clear cut whether something is defined, something is implied. Okay, no? So you need to make very clear cut what is defined, what is implied from what is defined. Okay. Yes. Right. So for this part, right? For this part, I can give you example like this, but when you go to higher level course, right, you should be able to imagine this in your mind by just me telling you this example here. Right. So once I tell you this example, Z mod PZ, immediately in your mind, pick a P, 5 3 or what, and then think of a possible polynomial, and then try and verify it. Okay, this is another skill you need to learn pure maths. Why people hard to learn pure maths? Because they just listen, they don't know what people are talking about. So once you listen what people say, you should make it into action. This is what pure maths is. Pure maths is not talking nonsense. Maybe some of them is just talking nonsense. I mean, a lot of them actually. But you have to be the one that can find truth between this and nonsense. Okay, yeah, that makes sense. This is what the pure maths can give you. If you ask about what pure maths can do, this is what pure maths can give you. Hard or not very hard, super hard. Super hard. Only until I'm the stage of 28, I understand this. But it doesn't imply that you have to go to 28. Now you have the chance. So please do it. Okay. Break. Okay, break. Let's break until 9. What time is it? 24.我说你要本怎么说来？可以。你看还是你要问东西？看。哦，你看。去看我出去走走。没有，他怎么说子？有些有，这个很好哎，但是他的喜欢我，你要看他们，他正反的，好像你说淘宝上便宜，淘宝是新华书店，新华还有。正反的，因为建筑变比的时候就是它就是它数学，是有。还有变，但是之前看起来很那个。还有是中国中国数要什么？这是一个比较样子啊。没有了。 到底参与这个比较难，这个就是我们好的，够。那个myself, I both oh, 那几点面都会去买最少天6分一个，是吧？是嗯，那个 intersection in universal set 是不是？有啊，有啊，有一个最大的 set。对，interface 什么对？哦。Yeah, let's take attendance, Venus, 隔天，星，规则，yes，安德，yes，严苛，OK，Steven，看了，诗雨，Seng，训灵，海人，呀，Info，Ryan，以兄，Seng，英奇，可以，雪岩，雪岩，OK，家燕。 by 原加 not here. So 文数 is 一定以为我本业行经节一周OK 英语 yes 友情真诚 yes 说你外语嘞啊 oversleep 哦 OK 一 yeah 千轩莹 Grace蔡燕嘉文明修 yeah Michelle 燕 Haley Sick 沈梅 yep 子源 was not here on okay. Oh, okay. Did you apply leave or you just I know, I mean, did you apply for leave or you just absent? Yeah, absent. Okay. Okay, let's continue. Hopefully today we'll get to an ideal. So next proposition. This proposition. Let's say we have a bunch of variable x and a bunch of variable y. Hello, Y, ready? Y. Last. Okay, let's pick two set of variables. The claim is there's an isomorphism. Okay. The isomorphism from R adjoint xy to R adjoint x and then adjoint y. Okay, which is the identity on R and which sense. You see, while I'm talking here, you should start quickly. Think, give me a set S1, S2, give me a Y, Y1, Y2. Okay, try and form this map here. Okay, so which sense what? Which sense what? The variables to themselves. Okay, quickly turn this into something that you can see. For example, what? Consider x equals to x1, x2, and perhaps y equals to y1, like this. Okay, and then the claim is you have a map R x1, x2, y1. There's an isomorphism between R adjoint x1, x2 first, and then adjoint. Okay, so when I talk about general segment, quickly form a example in your mind. Okay, quickly form an example. What is this set here? What is this R adjoint x adjoint y? What does this mean? What's this set actually? So when we talk about adjoint here, right? What is this? This is the coefficient of my polynomial ring. Okay, so for example, what is in second example here? Let's look at, for example, Rx, y. What's the polynomial here? What's the polynomial here? For example, y plus s squared plus 1y. Okay, or y squared. So this is a polynomial with coefficient in the ring of another polynomial. So s squared plus 1 is a polynomial in Rx. Make sense? Okay. But you also can view this element in R adjoint xy. Okay, how to view this element in this set here? We can rewrite this element as s squared y squared plus y plus y squared. Okay, so these two rings represent the equality here. Okay, make sense or not? Okay, so here is what you can use the combination product of xy to build your polynomial. Here it is. Use x squared times y squared, okay, plus y squared. So this is the element here. But if I do factorization, then you are living in another ring. And then the accent of the proposition tells you that these two rings are isomorphic because these two things are equal. Okay, one of them you just expand it out, the other you just collect the like term. Okay, so the factorization you do in high school turns to a ring statement here. Okay, no? This ring statement tells you what is your coefficient. The coefficient here is just R, 1, 1, 1. The coefficient here is what? Living in R adjoint x, 1, s squared plus 1. Make sense? Okay. If it is making sense, then we won't prove it. Because basically this is the proof. So, okay, let me briefly tell you what's going on. So inside the proof, right? So you have a phi. So define a phi such that your R is sitting in your R adjoint x, y. Okay, what you want to show? You want to show that these two are isomorphic. To show that two rings are isomorphic, when you talk about isomorphism, what do you need? You need a isomorphism. You need a adjective what? M. You need a start with M. You need a map. Very important in algebra, we talk about map. So what kind of map? A map, which is a homomorphism, which is bijective. So build a map. How to build a map between these two? Okay, how to build a map between these two? Just now, what do we introduce? Mathematics is in sequel, right? So what do I introduce before this proposition? What's the proposition I introduced before this one? You are like goldfish, huh? You know what is goldfish, huh? I thought 3 minutes. 3 minutes memory. After 3 minutes, you forgot everything already. Substitution principle. Okay. So substitution principle gives you a homomorphism. Okay. So I give you a homomorphism between two rings here. Okay. So we can take R prime here to be the new codomain we're looking at. For example, Rxy. Because R adjoint X adjoint Y, you can show that it is still a ring. Okay. So let's define this inclusion map here. So here is an inclusion map. You know what's the inclusion mean? Inclusion. So you include it in. Okay, so it means that you send R here to R. You send R to R. You just include it. So why is it an inclusion? You should similarly think of a picture. So you have a ring R. Okay, and then you include into a bigger ring, call it R adjoint X. It just do what it should do. This is called inclusion. It is not wrong. I draw this picture here because in future you will see that every commutative ring you can find a geometry to represent it. Okay. Yeah. Okay. All the commutative ring is equivalent to some geometry. Okay. Let's continue. So we have this definitely this inclusion of ring already. Then what can we do by the substitution principle? What do we do? What do we do? What should we do? We just do the really obvious thing. We just do xi to xi, yj to yj. Okay. We just do this. Okay, nothing special. Just do this. Xi to xi, yj to yj. Because si and yj are still in R adjoint x adjoint y. Yeah. And then by substitution principle, you get this homomorphism. Then how to show this is a bijection? How to do bijection? Quick, too slow. How to show bijection? And mind you, in the exam, again, you will need to show these things. Yeah, so what is a bijection? Need to show. Sorry? What do you need to show for bijection? Injective or surjective? By this case here, you should see that this map is invertible. This map is invertible. Okay. So you should find what is the inverse. What's the inverse? What's the inverse here? I said it's invertible, right? That means the inverse exists. What's the inverse? Inverse means what? You need to go back. How to go back? Sorry? Yeah, it is itself. So you just send Si back to Si, Yj back to Yj again. Yeah, it's the same. Okay or not? Okay. So there's nothing special here. It is exactly what this example tells you. Okay. But the more important thing here is the presentation here. Okay, it's the presentation of this, the form of this polynomial. Because the different way you present it is how you simplify the polynomial, right? Okay, so this will tell substantial amount about your rings. Yeah. So the corollary here is the division with remainder works for polynomials in, I would say, multiple variable or two variable, multiple variable. So last time we introduced division with remainder for the one variable polynomial ring. But you can see that for multiple variables, what can we do? We can adjoin the variable one by one. So you can do division one by one. Okay. In y first and then in x, then so on. Okay, so division with a remainder works. Okay. And continue. Let R be a ring. So this is a very important position because it tells you that there's always a unique homomorphism from the integer to ring. Okay, this is a very important position. Okay, why? Because the natural ring we think about is Z, and then Z can be included into any rings. Okay, how do I define this? Okay, how should I define this? What do you think? How should we define this? How should we define Cn for all the n greater or equal to 0? How do we define n? N to n? Does n exist in any ring or not? What's the thing that exists in any ring? Which identity? Additive identity? 0? You said to nothing.
I think nothing.
Huh?
Nothing.
No, there's one thing there. There's one thing you could try. You send to instead the multiplicative identity 1, and then do it n times. Why? Does multiplicative identity exist in any ring or not? Multiplicative identity, not inverse is identity. Don't confuse. Identity are not inverse. Okay, identity. So 1 must exist in your ring, and then your ring is closed under addition. So I can do 1 plus 1 plus 1 plus 1. Okay. Make sense or not? So every operation on the right here makes sense in any ring. Okay, so I can always do this. How about minus phi of minus and negative n? I just take negative of phi n. Yes, the inverse. Okay. So then you need to check that this is really defining a ring homomorphism here. Okay. So you need to prove that this defines a ring homomorphism. Or maybe I should put this for all phi n to the front. Yes.
So multiplicative identity
Mm.
and identity.
Why not? You can, yes. Because your ring is closed under addition. You form a abelian subgroup. Okay. So this addition here really depends on the addition in your ring. So if you have done the exercise in your assignment, you have addition on set, right? So you need to add the multiplicative identity using the addition you have. So for example, just now Jimbo try, right? The multiplicative identity for the intersection is the universal set. So what is universal set plus universal set plus universal set plus universal set? N times. Okay, for example, this is the example inside your question 5 in the assignment. Okay, make sense? Okay. Okay. We need to prove that this is a ring homomorphism. Okay. What's the property you need to check? P of use what notation? P of A plus B equal to phi A plus phi B. P of AB equals to phi A plus phi B. 3. Phi of 1 equals to 1. Okay. But in this case here, the third one is obvious, right? Because by definition. How about the other two? How about the other two? Why? Why is it obvious? How is it obvious? How's it obvious? I give you 2 integer. Why can I split it? Associativity, correct. Because of the associativity in your ring, right? Okay. But how about negative number? Do you need to deal with negative number? So you need to deal separately. So if it is, I think if AB is greater or equal to 0, I think it's obvious, right? Because what is C of A plus B? It's just 1 plus dot 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 plus 1 A plus B times. Then, like what makes you say, split it A times first and then B times. Right? How about if there's negative involved here? What should you do? Okay, you need to check. Okay, can I leave you to check? I'll prove it in my lecture now. Okay. Yeah. So how about for A less than 0 or B less than 0? Okay. Similarly for CAB. Okay, so this is similar. So you should try. And then I will leave the proof inside my lecture notes. Okay, let's keep going. By the way, if you want to stop me, just feel free to stop. Definition. This will lead to an ideal later. So again, we take a ring homomorphism. Still, the kernel of this map is still interesting. Okay, so we look at the kernel of phi. Okay, so these are all the things that get sent to 0 by phi. Okay, all the ring element that get sent to 0 by phi. Okay, it's the same. The proposition again, a ring homomorphism, okay, is injective. If and only if, want to guess? Yes, kernel of phi equals to identity. Which identity here? There's two identities here. The additive one. Okay, good exercise. Practice. Show this. Okay, not far different from the group one. Left to the readers. Okay, yeah, try and do it. Not too hard. But kernel is very interesting. Let's discuss a little bit about the kernel. Right? So obviously, this kernel phi is closed under addition and multiplication. Does it make sense? Does it make sense or not? Can you imagine what I said? So like phi A plus B should go to 0. Why? By ring homomorphism, this is just phi A plus phi B. But if A and B are in kernel, both of them evaluate to 0. Okay. Similarly for phi AB. Okay, so this one is if AB in the kernel of B. Similarly for phi AB, you get phi A dot phi B. 0 times 0, you get 0. Actually, there's another property of this kernel. Okay, it's very special about this kernel here. So this is a very important property you need to know. Okay, there's one special property here. If I take any element, okay, in my kernel phi, and literally any element in my ring, what happened to Rx? What happened to phi Rx? Phi Rx is what? Phi Rx equals to phi R times phi X. Phi X is what? 0. I don't care what happened to phi R. This thing will always get sent to 0. This is the special about the kernel in a ring homomorphism. The kernel in groups is what? Is a subgroup. Not just a subgroup, it's very special subgroup. Normal subgroup. And then normal subgroup is try to generalize the kernel because at the end we show that every normal subgroup can be realized as some kernel. This case is the same. We want to generalize the idea of a kernel again. Okay, which is what we call the ideal. Yes, ideal. You know what ideal is? I think the Chinese translation is 美好. Seriously, 美好.不, sorry, not 美好. A synonym to 美好, 理想. Okay, it's the ideal thing. It's the ideal. It's the like dream, right? It's a dream. And 理想. Okay, yeah. When I go to the Chinese conference, right, they say 理想. Then I was thinking, okay, ideal. Yeah, ideal. So ideal of a ring R is a non-empty subset. With the following property. First of all, it is closed under addition. And then second of all, if X is in I and R is in R, then Rx is in. Okay, so note that I didn't mention that closed under multiplication, right? Why? Why didn't I say closed under multiplication? Sorry? This is not necessarily a subring. This is not necessarily a subring, but it's not about that reason there. Because, okay, yeah, this is not a subring. Okay, I want to stop there first. So why I didn't mention close under multiplication? Just now the kernel close under multiplication, right? So why I didn't mention that? Yeah, specifically. Why? Sorry? Everything goes to zero? No, nothing goes to zero here. This is just a definition of a set. Why I didn't say I have to be close under multiplication? Right? So yeah, the axiom 2 here is much more general. It is close under taking any element in R. I is a subset in R. Right? It's included here already. This is more general statement. Okay. So if you have more general statement, you don't need to go do redundant stuff. Okay, you don't need to add. It is closed under multiplication. Why they call this ideal? This is coming from number theory. Okay, they want to find a number field that you can do unique factorization, meaning 6 have to be 2 plus 3, 2 times 3, for example. Okay, and then these ideals will help you to split elements of another ideal inside the ring. Okay. Yeah, for example, 2 and 3 is the ideal for 6, like that. Okay. But 6 doesn't always split into 2 and 3 in different ring. For example, how to make 6? You can take 1 minus square root 5 times 1 plus square root 5. So if we live in a different ring, then this 6 can be represented in 2 different ways. 2 times 3, or 1 minus square root 5 times 1 plus square root 5. Okay. And then these things form ideals if you go deeper in the algebraic number theory. So we turn the study about just number, okay, multiplication of number, into study of rings. Okay. Later we'll see more example of ideal, and then how do we play with our ideals. And then we can take, last time we take quotient by normal subgroup, right? So now we can take quotient by idealism. And what's a quotient rings? And this is a very important subject to close the ring topic. Okay. All right. So we'll see you on next week. Yeah.
And 3 ring.
Free rings. Free rings. Not really, but we have free modules. It's the more generous. Yeah, free module.